Swayam Prabha. Digital India. Educated India.
Welcome. So, we are in the second lecture of module 9. So, here we will just in the last class we have just studied the 2D elasticity problem and its weak form, how weak form has come. So, also we have also studied the variational formulation, means in fact the energy variation we have studied also. So, that also I have given you the equations, and in this lecture basically from weak form to matrix form, that is because these are the vector problems. So, the your variables are two-dimensional domain, and variables are not only a scalar variable rather than a vector variable, that is u and v. For our case, for the present case, u and v are the displacements. Now, in this lecture we will try to find out how we can go from the weak form to the matrix formulation, because matrix formulation is important because you need to code this in computer. So, matrix formulation will be easier to compute. Now, then I will discuss for the stiffness matrix and force matrix for the CST element. So, we have studied the CST element. CST element is constant strain triangle. So, now to start with, so what we are doing, actually we are doing the 2D elasticity domain, the problem which has two distinct boundaries, that is one is traction boundary, one is your lambda u, that is displacement boundary. So, displacement boundary may be fixed like this or something like this, means I mean the where the displacement is prescribed, and then there is a force. So, applied force or the traction force. So, T has two component, Tx and Ty. So, and the body is maybe having a body force in terms of Fx and Fy. So, F is the body force. So, now the governing equation for this system is also, we know that and the density rho is the body. Now, we know all the governing equation for this problem and the boundary condition. For instance, in lambda t you have the boundary condition of sigma xx nx plus sigma yy sigma xy ny equals to tx, and sigma xy ny nx plus sigma yy ny equals to ty. So, we know this, and the boundary condition for the Dirichlet domain or the displacement domain is u is prescribed as u bar, v is prescribed as v bar. So, this is given. Now, so these tractions in terms of point load is possible, in terms of pressure is possible. So, every thing is scattered into this generalized boundary condition. Now, we have studied the weak form. So, I will just start from the weak form where we have just left. So, our weak form looks like this. That is, again we are following a linear elastic constitutive matrix, that is sigma is a if I write it in vector form, sigma yy, sigma xy, and then you have your constitutive equation is sigma multiplied by the sigma vector multiplied by the matrix C and then the epsilon vector. Epsilon contains the epsilon xx, epsilon yy and 2 epsilon xy. So C contains C11, C contains like this, C is a matrix. So this is linear elastic constitutive equation. Now this is not specific for the isotropic case. You can modify this thing in terms of Young's modulus and Poisson's ratio for isotropic case, and this is also valid for the orthotropic case. So now this equation is linear elastic constitutive equation. So what was our weak form? Our weak form looks like this. For two-dimensional problem, we have to multiply with h, the thickness of this body. So h is the thickness, then integral over the omega or v, whatever you call. Now this is we have two weight functions w1 and w2. So our this thing looks like this. Weak form is c11 del u del x plus c12 del v del y plus del w del w1 del y and your c66 del u del y plus del v del x, and then you have the inertia term, that is your due to the mass and inertial effect of the body. So no, you have the forcing term, so body force term fx w1 fx, then you have the inertia term, that is rho into your u double dot, that is the acceleration, u acceleration. You have two axes, that is x and y. So this is your axis and this is the vector displacement vector u. So and v. So now the component of the displacement vector u and v. Now this is multiplied with w1. So this is the volume integral. So this will be multiplied by dx dy. So now I can change this thing as my omega is the two-dimensional domain. So this is my your volume integral. Now you have additionally boundary condition you will have. So the boundary condition will be like this, minus h again. So boundary term will contain on the surface. So lambda t boundary. So lambda is the domain, that is gamma is the domain, and then you have the this boundary condition, that is sigma x x n x, sigma x y n y, so which is coming from the weak form. So that if I write it, then that is your del w, w1 will be multiplied. So that is w1 is multiplied, and then you have your c11 del u del x plus c12 del v del y multiplied by your nx. So that is your first term for the boundary, and then you have again this sigma xy term will be there. So if I write that, then this is c66 del u del y plus del v del x into ny. So this is integrated over the surface, that is not here, the surface is a line. So this line, along this line you have to integrate. So this is the how we calculate traction vectors. So now this is the first equation. So this equation must be goes to 0, must go to 0, and the second equation again for the domain is, again we have a second weight functions, that is dw2 by dwx, then you will have c66 del u del y plus del v del x plus you will have del 2 omega 2 by del y. Then you will have the second strain term, that is epsilon yy, second stress term, that is epsilon yy. So C12 del u del x plus C22 del v del y. So this is my stress of the internal term, and then W2 Fy plus rho V double dot into W2, then it will be again dx dy. Then again you will have the boundary condition. Boundary conditions will have the similar to this. You will have W2 and then you will have first sigma xy term. So C66 del u del y plus del v del x into nx plus C12 del u del x plus C22 del v del y into ny. So this is multiplied by ds. So this is the this is equals to 0. So this is the weak form that we have studied. Now from the weak form, if I want to deduce the discretization, then the body has to discretize with the element. So let us discretize. You can discretize with triangular element or rectangular element or even quadrilateral element or the higher order element. So if you discretize with triangular element, for instance, if the CST, the linear strain triangle, constant strain triangle, that is your node 1, node 2, node 3, all nodes will have two variables, 2 degrees of freedom, that is u1, v1, and then again you will have u2, v2, then you will have u3, v3. So similarly, if you discretize with rectangular element, for instance, then you will have 4 such values. So now this is my 1, 2, 3, 4. So you will have 4 such you will have 4 such displacements. So this is my displacement u1 v1, u2 v2, and so on. So now you will have per element, the degrees of freedom per element you will have for rectangular element, for triangular element you will have 6 degrees of freedom. So 6 degrees of freedom. For each node there are 2 degrees of freedom. Similarly, it will have 8 degrees of freedom. So as we have seen that from the previous knowledge, that our stiffness matrix or the elemental stiffness matrix will be 6 cross 6 for triangular element, and for rectangular element it will be 8 cross 8. So now the interesting thing is that it depends on the shape functions. So our shape function means the number of element and number of degrees of freedom. So if for any rectangle or a triangle, I can write my shape functions as summation of j equals to 1 to n, say phi j uj. So this is the u displacement discretization. Similarly, you will have v displacement, that is summation of j equals to 1 to n psi j uj, sorry, vj. So vj. Now this discretization, if I just plug into this weak form, then I will get the matrix equation. Now this discretization, if you look carefully, that this psi for both the variable, that is u displacement and v displacement, are same. So that is, it is also this u displacement, that is u, its function of xy is similar way v is a function of xy. So psi j are function of xy. For instance, if you want to use the triangular element, then the triangular element degrees, the shape functions, you already know what is the psi for triangular element for CST, constant strain triangle. So psi I is actually like this, alpha I, this is 1 by 2 AE, 1 by 2 AE. A is the elemental area of this triangle, and then this is alpha I plus beta I x plus gamma I y. So this is a linear triangle. So alpha, beta, gammas are based on the coordinates of these 3 points. So alpha I is actually x j y k minus y k minus x k y j, and beta I is actually yj minus yk, and gamma I is actually minus xj minus xk. So now here alpha ijk are not I not equals to j not equals to k, and ijk are permutation in natural order. So that is 1 2 3 means 2 3 1 and then 3 1 2 like this. So in natural permutation, natural order permutation. So now so that is this alpha, beta and gamma j are essentially constant. Once you, for a body, if you want to discretize it with the triangular element, for instance, I am discretizing this. So this body, now once I fix my discretization or fix my nodes, I know the coordinates of these nodes. So this is xy coordinate system. So alpha, beta and gamma, alpha 1, beta 2, alpha 1, alpha 2 and alpha 3, beta 1, beta 2, beta 3, everything I know from the discretization, because it is entirely dependent on the display coordinate of the triangle or coordinate of the nodes essentially. So I know everything. So only variable is x and y. So phi I again is a function of psi I is a function of x and y. So now with this I can now this plug into this weak form, and then I can simply formulate the weak form. So if I plug into this, then my matrix equation will look like this. So M again 0 0 M, then this is my u dot, u double dot, v double dot, right, and then plus your the stiffness matrix, that is K11, K12, K12 transpose, then K22. So why K12 transpose? Because this weak form, if you do the this bilinear form, is actually symmetric. So that's why the symmetric stiffness matrix will come. So now this is my u and v. So this is my then I will have my force vector, that is F1 and F2, or whatever you call. So now F1 and F2 will contain two terms essentially, one due to the body force term and one due to the traction vector, that is the natural boundary term. So if I do this M, what will be the Mij? So look, M is a so this matrix is essentially a 6 by 6 matrix. This is also a 6 by 6 matrix. This is also a 6 cross 1 vector. So naturally M will be a 3 cross 3 matrix. So this 3 cross 3 matrix, if I write, then from the weak form I write this is the term which is responsible for the inertial term. So, this term and this term is for the inertial term. Now, here W1 and W2 I will assume the same as we do it for the Rayleigh-Rince or Galerkin method, that is psi I and psi j. So, all W1 and W2 or the Bubnov-Galerkin what we have studied, that is the same, the interpolating function and the weight functions are same. If I assume that, then Mij I can simply write rho h, rho comes from here and h comes from here, psi I, psi j, right? Because here u is again interpolated in terms of psi j uj, and psi I is the weight function. So, this is how we get the, so this is integrated over dx and dy. Look, this psi I and psi j are the function of x and y. So, only this integration can be performed exactly for the triangle. Now, similarly, if I want to find out k11, then k11 term will come here. So, only u term will be, so k11 and u. So, that is your, so if I write now, this is omega e. So, this is omega e. Omega is my elemental area. So, omega e is essentially AE. So, AE. So, the area of that element. So, over the area integral. So, again I will have my h from here, and so the first term will be del psi I by del x, then we will have C11, then again we will have del psi j del x, and so this term will be this term and this term, and then again this term, due to this term it will be there. So, again I have to then plus del psi I del y into C66, again del psi j del y. So, this is my k11, and this is again dx dy. So, h is multiplied with the whole body. So, generally we take h constant, but variable h is also possible. So, this is the first term k11. Similarly, I can find out k12. So, if I want to find out k, so this is ijth term. Now, k12 ijth term, that is also I can write. So, from the first equation, which quantities will be responsible? The responsible quantities will be this quantity and this quantity, this quantity. So, these two quantities will be responsible for k12. So, if I write the similar way, that is h will be multiplied integral over omega e, and then I will have del psi I by del x into C12, then we will have del psi j del y. So, this term will be there. So, due to this term C12 del psi j del y, and then del psi I by del y into C66 del psi j del x. So, these two terms will be there. So, plus C66 del psi I by del y into C66 into del psi j del x. So, this is coming from here. Now, similarly, if I, so this is again dx dy. So, this is essentially, if you transpose it, so k12 transpose we know. So, now the next k22 again we can find out k22 ij. So, k22 ij will have again h multiplied and then over omega e, then we will have your these two term, that is del psi I by del x into C66 del psi j del y plus, so this will be sorry, not del psi j del y, because del psi j del x term will be there, because it is y term, del x term. So this term will be there. So this term and this term will be there, right? Because these two terms will go to the K12 transpose. So now this multiplied by del psi I by del y into C22 del psi I by psi j by del y, this term. Now this multiplied by dx dy. So you know these quantities. Now you will have the force vector. The force vector F1I will contains again H. The first integral will be due to the body force. That body force term is given here, W1 psi Fx. So that is your W1 means psi I Fx. So Fx can be function of x, Fx can be function of y, or Fx can be function of both of x, or Fx can be constant. So psi I your this term, so W1 Fx. So this will be Fx will be just, I will be writing this Fx because it can be function of x. Now this is again multiplied with dx dy, and this is again volume area integral here, or the surface over two-dimensional surface, and then you will have your this quantity, this traction vector. Now while doing the traction, if you look carefully, that this is nothing but, this quantity is nothing but sigma xx nx. So this is nothing but sigma xx nx, and so this is nothing but sigma xx nx, and this quantity is nothing but sigma xy ny. So sigma xy ny. So this I can replace by txw1. So now this is, if I write that, then you will have your integral over the lambda e, that is the boundary of the element, and then again multiplied by h tx w1. So w1 is again psi I and tx. So tx. Now this integral is over ds. So similarly f12 is integral over omega e, then psi I, sorry, this is f2I. So psi I into your fy dx dy minus h into psi I into your ty ds. So this ds again will be, so this is the boundary of the element gamma e. So this is the matrix, the how to form the matrix. But again this thing we can very easily find out again from the virtual displacement equation. If you remember the virtual displacement equation that we have studied in the previous class, that is your integral over the volume, that is your sigma ij, variation of strain ij, plus your rho ui double dot into delta ui, that is over dv minus your integral fi, so delta ui dx. So this is dv, and this is all over volume. Then you have this minus ti into delta ui, so traction contribution over gamma, then that is equals to ds or d gamma, whatever you call. So that is you can write ds also, that is also fine. So ds that is equals to 0. Now if I do it for the plane stress problem, then plane stress problem, if I write this equation, then it will look like this, that is integral. So for plane stress case, so this virtual work statement will look like that integral your sigma xx del epsilon xx plus sigma yy del epsilon yy plus sigma xy to sigma xy del epsilon xy, right, plus your rho u double dot delta u1, or not delta u1, so let us write u and v, delta u plus rho v double dot delta v. Now this minus by f x delta u plus fy delta v, right, and then this again the integral I can transfer to dx dy, and I can write omega e elemental quantity, so dx dy, and then again minus integral tx delta u plus ty delta v. So this again over surface gamma. So now this is the plane stress case. So I can write this thing easily in matrix form. So this omega e, I can write it that del epsilon xx del epsilon yy and del epsilon xy I can write, so 2 I can write here, and then this is I can write as transpose, then you will have sigma. So sigma xx, sigma yy, sigma xy. So this into dx, so this plus your this quantity, so rho again I can write delta u delta v transpose into your rho if I take outside u double dot v double dot. So this I can write very easily from the this equation. Now here again this quantity also I can write like this, that is your delta u and delta v transpose into your fx fy, so into dx dy, then minus integral over gamma, then this is again delta u delta u delta v transpose dx dy. So this is over ds, this equals to 0. So I write this thing in a matrix equation. Now we know what is my for CST element. So for CST we know u and v. So u is psi 1 u1 plus psi 2 u2 plus psi 3 u3, right, and then for v is again psi 1 v1 plus psi 2 v2 plus psi 3 v3. Now if I do this, then I can evaluate del u del x, right, and del v del y, and then del u del x del y and del v del x. So these quantities I can easily find out, and since this is psi is a linear function of x, so this quantity will be constant term. So because differentiation of a linear function is a constant. So now u and v I can write like this. So in a matrix form, so if I write this, that is shape function matrix. So what I will write in terms of u1, u2, u3, v1, v2, v3. So I will have psi 1, say 0, psi 2, then again 0, then psi 3, again 0, then 0, psi 1, 0, psi 2, 0, psi 3. So this multiplied by your u1 v1, u1 v1, u2 v2, u3 v3. So this is how we write the u and v together. So let us call this is delta. So delta is a vector which is uv or okay, let me not call it delta. So now let us say this is my psi matrix. So psi matrix multiplied by a vector which is delta. So now this is my delta contains the all displacement degrees of freedom. Now this again, if I want to find out strains, so again I can find out epsilon xx, epsilon xx, epsilon yy, epsilon xy. So strain matrix I can find it out like this. So this matrix will be again a matrix which is derivative of this matrix. So now the quantities, the strain matrix I will have, so B into delta. So how to calculate B? So now epsilon xx is essentially del u del x. So del u del x we know. So del u del x means it is derivative of psi 1, derivative of psi 2, derivative of psi 3. So like this we can compute the B matrix. So each component of B matrix I can calculate. So now similarly I can do the stress matrix, that is sigma xx, sigma yy and sigma xy. That also I can find it out. So that is again I have C matrix into epsilon matrix, that is constitutive equation. C matrix, epsilon matrix I can write now C and then again B and then again delta. So this is known as the strain displacement matrix. Strain displacement matrix. Right. So this the strain displacement matrix also we can write in this form, that the strains essentially we can write in this form, that is delta del x 0 0 del y, then del y del x multiplied by u. So u and v. So this is my strain matrix. So now here this strain matrix again, if I call this matrix as T matrix, then I'll have u and v. From here I can write this as psi and delta. So this T multiplied by psi is my B matrix. So this is how we compute B matrix. So it is just derivative so this is a 3 cross 2 matrix. This is now so this is a 3 cross 2 matrix, and this is a your for 3 noded triangle. So this is a 2 cross 6 matrix. So this is a 2 cross 6 matrix, and delta obviously is a 6 cross 1. So B matrix dimension will be 3 cross 6 matrix, right? So once we know B matrix, then we can substitute it for stress matrix, and then pre-multiplied with the constitutive matrix we can get the stress. Now once we know this, then we need to have the variations. So how to compute the variations? So again delta u, likewise we have discretized the displacement, we can discretize the variations also. So delta u which is a function of xy, so variation of xy u, so we can write it psi 1 delta u1 plus psi 2 delta u2 and psi 3 delta u3, and similarly delta v, I can write the variations is psi 1 delta v1 plus psi 2 delta v2 plus psi 3 delta v3. So essentially the variations which as function that can also be discretized. So if I do that, then my delta u and delta delta u and delta v, I can again delta u and delta v, I can represent in terms of matrix, which is again a psi matrix multiplied by the variation delta w, delta, right. So this again similarly we can compute the variation of strains. So delta epsilon matrix, so delta epsilon matrix will be similar to this. So this matrix again B matrix into the variation of delta. So I know everything. Now if I plug this information to this virtual work equation, then what I will get? I will get is integral. So integral h will be there, then delta epsilon will be delta epsilon transpose. So delta transpose B transpose, then again I will get this sigma xy and sigma x yy and sigma xy. So C B delta. So now C, then again B, then again delta, this is dx dy, right. And then again I will get the inertia terms here for the inertia terms. So rho u again, so plus rho, so this is over this, so rho, then again what I will get, delta u is your psi, so delta transpose again B transpose, sorry not B transpose, psi transpose, because this is nothing but your, this is nothing but delta u delta V transpose. So psi transpose, so that is your psi matrix, this is transpose. Now this multiplied by your again u double dot V double dot. Now u is a function of now u1 u2, so that is psi matrix or u delta so u is u and v is essentially psi matrix into delta, right. So now u double dot v double dot is essentially psi matrix is not a function of time because it contains shape function. So then again delta double dot, delta double dot means the nodal acceleration. So now this multiplied by your psi matrix into delta double dot. So this completes our mass and stiffness matrix, and then again I will get from here that delta this thing and fx fy. So delta this thing is again psi transpose minus integral over omega e, then psi so h will be there, so psi transpose, so delta transpose psi transpose into your fx fy, so f vector, and this is again dx dy. So again I will have the traction boundary condition, which is again over lambda E. Then we will have delta delta transpose into psi transpose. Then again we will have traction vector Tx and Ty. So this is the matrix formulation. Now this equation must go to 0. So now if I take the delta delta transpose common from all the equation, delta delta transpose if I take common, then arbitrariness of delta delta will give me the elemental equation. So if I take this thing out and consider the arbitrariness of delta delta, then I will get the equation which is K elemental stiffness into delta. So this is the first term, and so remember delta is the nodal variable, and then what we'll have is rho H, or the, let me call it mass matrix ME, and then you will have the acceleration term delta double dot, right? And then what we will have is your force vector, so that is equals to your let us say F matrix. So F vector, let me, since I have represented it in capital, so let me write as F. Due to this is my F, and then again due to this I will have, this is Fe, and then this will have QE that we have observed earlier. So this is my QE. So this is my equation. So now here if you look this equation and the matrix equation, it is same. So here if I have divided it into two palm, one is small f and capital F and Q. So here I have written it in the same thing. So let me now, let me since I have the whole thing is E, and then this whole thing is Fe. So this is my governing elemental equilibrium equation for the dynamic case. Now what is my Ke now? My Ke will become integral over H. H can be function of x. So B transpose C B dx dy. This is my K matrix. And then what is my ME matrix? ME matrix will be H integral of psi transpose psi. So there will be rho multiplied here. So rho psi transpose psi dx dy. And what is my F matrix? Fe vector, which is H integral over, these are volume integral, right? And these are surface or the line integral for 2D. No, this is volume integral, this, because this is body force. So this is my psi transpose Fx Fy. This is my dx dy. And then what is my QE? QE is my H integral. This is my line integral, right? So this is my psi transpose into your Tx Ty. So this is the complete process of the stiffness equation. Now if I don't consider the dynamic equation, that means if I neglect the inertial effect, then it is simply K delta equals to F. Now as we know the elemental equation, then we can assemble it and then we can solve it after putting the Dirichlet boundary condition or the displacement boundary condition. Now then it comes into the post processing, that is once you find out the displacement, what will be the stresses, what will be the strains. So those things. So for this thing it is very easy, because CST element means constant strength, element wise it will be constant, so naturally stress will be constant, so element wise it will be constant, so unless the material property varies. So now here I stop today. In the next class I will just show in detail how to compute this traction vector and the or the internal force vector, how to compute this and force vector, and then we'll try to solve some problem. So after doing the quadrilateral stuff. So I stop here today. So thank you.